The Moon is an astronomical body that orbits Earth as its only natural satellite. It is the fifth largest satellite in the solar system and the largest among planetary satellites relative to the size of the planet that it orbits, its primary. The Moon is, after Jupiter's satellite Io, the second-densest satellite in the solar system among those whose densities are known. The Moon is thought to have formed about 4.51 billion years ago, not long after Earth. The most widely accepted explanation is that the Moon formed from the debris left over after a giant impact between Earth and a Mars-sized body called Theia. New research of moon rocks, although not rejecting the Theia hypothesis, suggests that the Moon may be older than previously thought. The Moon is in synchronous rotation with Earth and thus always shows the same side to Earth, the near side. The near side is marked by dark volcanic maria that fill the spaces between the bright ancient crustal highlands and the prominent impact craters. After the Sun, the Moon is the second brightest regularly visible celestial object in Earth's sky. Its surface is actually dark, although compared to the night sky it appears very bright, with a reflectance just slightly higher than that of worn asphalt. Its gravitational influence produces the ocean tides, body tides, and the slight lengthening of the day. The Moon's average orbital distance is 384,402 kilometers, 238,856 mi, or 1.28 light seconds. This is about 30 times the diameter of Earth. The Moon's apparent size in the sky is almost the same as that of the Sun, since the star is about 400 times the lunar distance and diameter. Therefore, the Moon covers the Sun nearly precisely during a total solar eclipse. This matching of apparent visual size will not continue in the far future because the Moon's distance from Earth is gradually increasing. The Moon was first reached in September 1959 by the Soviet Union's Luna 2, an unmanned spacecraft, followed by the first successful soft landing by Luna 9 in 1966. The United States NASA Apollo program achieved the only manned lunar missions to date, beginning with the first manned orbital mission by Apollo 8 in 1968 and 6 manned landings between 1969 and 1972, with the first being Apollo 11 in July 1969. These missions returned lunar rocks which have been used to develop a geological understanding of the Moon's origin, internal structure, and the Moon's later history. Since the 1972 Apollo 17 mission, the Moon has been visited only by unmanned spacecraft. Both the Moon's natural prominence in the earthly sky and its regular cycle of phases as seen from Earth have provided cultural references and influences for human societies and cultures since time immemorial. Such cultural influences can be found in language, lunar calendar systems, art, and mythology. Name and etymology. See also: List of lunar deities. The Moon, tinted reddish during a lunar eclipse. During the lunar phases, only portions of the Moon can be observed from Earth. The usual English proper name for Earth's natural satellite is the Moon, which in non-scientific texts is usually not capitalized. The noun moon is derived from Old English mna, which, like all Germanic language cognates, stems from Proto-Germanic mno, which comes from Proto-Indo-European mhn%s moon, month, which comes from the Proto-Indo-European root met to measure, the month being the ancient unit of time measured by the moon. Occasionally, the name Luna is used. In literature, especially science fiction, Luna is used to distinguish it from other moons, while in poetry, the name has been used to denote personification of Earth's moon. The modern English adjective pertaining to the Moon is lunar, derived from the Latin word for the moon, luna. The adjective selenic, usually only used to refer to the chemical element selenium, is so rarely used to refer to the Moon that this meaning is not recorded in most major dictionaries. It is derived from the ancient Greek word for the moon a tilde selen, from which is however also derived the prefix seleno, as in selenography, the study of the physical features of the Moon, as well as the element name selenium. Both the Greek goddess Selene and the Roman goddess Diana were alternatively called Cynthia. The names Luna, Cynthia, and Selene are reflected in terminology for lunar orbits in words such as Apollune, Paracynthian, and Selenocentric. The name Diana comes from the Proto-Indo-European diuio, heavenly, which comes from the PIE root diu to shine, which in many derivatives means sky, heaven, and God, and is also the origin of Latin dies, day. Formation. Main articles: Origin of the Moon, Giant Impact Hypothesis, and Circumplanetary Disk. The Moon formed 4.51 billion years ago, some 60 million years after the origin of the solar system. Several forming mechanisms have been proposed, including the fission of the Moon from Earth's crust through centrifugal force, which would require too great an initial spin of Earth, the gravitational capture of a pre-formed Moon, which would require an unfeasibly extended atmosphere of Earth to dissipate the energy of the passing moon, and the co-formation of Earth and the moon together in the primordial accretion disk, which does not explain the depletion of metals in the moon. These hypotheses also cannot account for the high angular momentum of the Earth-Moon system. File Evolution of the Moon.ogv. The Evolution of the Moon and a Tour of the Moon. The prevailing hypothesis is that the Earth-Moon system formed after an impact of a Mars-sized body, named Theia, with the proto-Earth giant impact. The impact blasted material into Earth's orbit, and then the material accreted and formed the Moon. The Moon's far side has a crust that is 50 kilometers (31 mi) thicker than that of the near side. This is thought to be because the Moon fused from two different bodies. This hypothesis, although not perfect, perhaps best explains the evidence. 18 months prior to an October 1984 conference on lunar origins, Bill Hartmann, Roger Phillips, and Jeff Taylor challenged fellow lunar scientists. You have 18 months. Go back to your Apollo data, go back to your computer, do whatever you have to, but make up your mind. Don't come to our conference unless you have something to say about the moon's birth. At the 1984 conference at Kona, Hawaii, the giant impact hypothesis emerged as the most consensual theory. Before the conference, there were partisans of the three traditional theories, plus a few people who were starting to take the giant impact seriously, and there was a huge apathetic middle who didn't think the debate would ever be resolved. Afterward, there were essentially only two groups: the giant impact camp and the agnostics. Giant impacts are thought to have been common in the early solar system. Computer simulations of giant impacts have produced results that are consistent with the mass of the lunar core and the angular momentum of the Earth-Moon system. These simulations also show that most of the moon derived from the impactor rather than the proto-Earth. However, more recent simulations suggest a larger fraction of the moon derived from the proto-Earth. Other bodies of the inner solar system such as Mars and Vesta have, according to meteorites from them, very different oxygen and tungsten isotopic compositions compared to Earth. However, Earth and the moon have nearly identical isotopic compositions. The isotopic equalization of the Earth-Moon system might be explained by the post-impact mixing of the vaporized material that formed the two, although this is debated. The impact released a lot of energy, and then the released material re-accreted into the Earth-Moon system. This would have melted the outer shell of Earth, and thus formed a magma ocean. 4546 Similarly, the newly formed moon would also have been affected and had its own lunar magma ocean. Its depth is estimated from about 500 kilometers (300 miles) to 1,737 kilometers (1,079 miles). While the giant impact hypothesis might explain many lines of evidence, some questions are still unresolved, most of which involve the moon's composition. In 2001, a team at the Carnegie Institute of Washington reported the most precise measurement of the isotopic signatures of lunar rocks. To their surprise, the rocks from the Apollo program had the same isotopic signature as rocks from Earth, however they differed from almost all other bodies in the solar system. Indeed, this observation was unexpected because most of the material that formed the moon was thought to come from Theia, and it was announced in 2007 that there was less than a 1% chance that Theia and Earth had identical isotopic signatures. Other Apollo lunar samples had in 2012 the same titanium isotopes composition as Earth, which conflicts with what is expected if the moon formed far from Earth or is derived from Theia. These discrepancies may be explained by variations of the giant impact hypothesis. Physical characteristics. The moon is a very slightly scalene ellipsoid due to tidal stretching, with its long axis displaced 30 degrees from facing the Earth due to gravitational anomalies from impact basins. Its shape is more elongated than current tidal forces can account for. This fossil bulge indicates that the moon solidified when it orbited at half its current distance to the Earth and that it is now too cold for its shape to adjust to its orbit. Internal structure. The moon is a differentiated body. It has a geochemically distinct crust, mantle, and core. The moon has a solid iron-rich inner core with a radius possibly as small as 240 kilometers (150 mi) and a fluid outer core, primarily made of liquid iron, with a radius of roughly 300 kilometers (190 mi). Around the core is a partially molten boundary layer with a radius of about 500 kilometers (310 mi). This structure is thought to have developed through the fractional crystallization of a global magma ocean shortly after the moon's formation 4.5 billion years ago. Crystallization of this magma ocean would have created a mafic mantle from the precipitation and sinking of the minerals olivine, clinopyroxene, and orthopyroxene, after about 3/4 of the magma ocean had crystallized, lower density plagioclase minerals could form and float into a crust atop. The final liquids to crystallize would have been initially sandwiched between the crust and mantle, with a high abundance of incompatible and heat-producing elements. Consistent with this perspective, geochemical mapping made from orbit suggests the crust of mostly an orthosite. The moon rock samples of the flood lavas that erupted onto the surface from partial melting in the mantle confirm the mafic mantle composition, which is more iron-rich than that of Earth. The crust is on average about 50 kilometers (31 mi) thick. The moon is the second-densest satellite in the solar system, after Io. However, the inner core of the moon is small, with a radius of about 350 kilometers (220 mi) or less, around 20% of the radius of the moon. Its composition is not well understood, but is probably metallic iron alloyed with a small amount of sulfur and nickel. Analyses of the moon's time-variable rotation suggest that it is at least partly molten. The topography of the moon has been measured with laser altimetry and stereo image analysis. Its most visible topographic feature is the giant far-side South Pole Aitken Basin, some 2,240 kilometers (1,390 mi) in diameter, the largest crater on the moon, and the second largest confirmed impact crater in the solar system. 6061 at 13 kilometers (8.1 mi) deep, its floor is the lowest point on the surface of the moon. The highest elevations of the surface are located directly to the northeast, and it has been suggested might have been thickened by the oblique formation impact of the South Pole Aitken Basin. 63 other large impact basins, such as Imbrium, Serenitas, Chrysium, Smithii, and Orientale, also possess regionally low elevations and elevated rims. The far side of the lunar surface is on average about 1.9 kilometers (1.2 mi) higher than that of the near side. The discovery of fault scarp cliffs by the Lunar Reconnaissance Orbiter suggests that the moon has shrunk within the past billion years by about 90 meters (300 feet). Similar shrinkage features exist on Mercury. A recent study of over 12,000 images from the orbiter has observed that Mare Frigoris near the North Pole, a vast basin assumed to be geologically dead, has been cracking and shifting. Since the moon doesn't have tectonic plates, its tectonic activity is slow, and cracks develop as it loses heat over the years. The dark and relatively featureless lunar plains, clearly seen with the naked eye, are called Maria, Latin for seas, singular mare, as they were once believed to be filled with water. They are now known to be vast solidified pools of ancient basaltic lava. Although similar to terrestrial basalts, lunar basalts have more iron and no minerals altered by water. The majority of these lavas erupted or flowed into the depressions associated with impact basins. Several geologic provinces containing shield volcanoes and volcanic domes are found within the near-side Maria. Almost all Maria are on the near side of the moon and cover 31% of the surface of the near side 69, compared with 2% of the far side. This is thought to be due to a concentration of heat-producing elements under the crust on the near side, seen on geochemical maps obtained by Lunar Prospector's gamma-ray spectrometer, which would have caused the underlying mantle to heat up, partially melt, rise to the surface and erupt. Most of the moon's mare basalts erupted during the Imbrian period, 3.0–3.5 billion years ago, although some radiometrically dated samples are as old as 4.2 billion years. Until recently, the youngest eruptions, dated by crater counting, appeared to have been only 1.2 billion years ago. In 2006, a study of Ina, a tiny depression in Lake Asphalt, found jagged, relatively dust-free features that, because of the lack of erosion by infilling debris, appeared to be only 2 million years old. Moonquakes and releases of gas also indicate some continued lunar activity. In 2014, NASA announced widespread evidence of young lunar volcanism at 70 irregular mare patches identified by the Lunar Reconnaissance Orbiter, some less than 50 million years old. This raises the possibility of a much warmer lunar mantle than previously believed, at least on the near side, where the deep crust is substantially warmer because of the greater concentration of radioactive elements. Just prior to this, evidence has been presented for two 10 million years younger basaltic volcanism inside Lowell Crater, Orientale Basin, located in the transition zone between the near and far sides of the moon. An initially hotter mantle and/or local enrichment of heat-producing elements in the mantle could be responsible for prolonged activities also on the far side in the Orientale Basin. The lighter-colored regions of the moon are called Theia, or more commonly highlands, because they are higher than most Maria. They have been radiometrically dated to having formed 4.4 billion years ago and may represent plagioclase cumulates of the lunar magma ocean. In contrast to Earth, No major lunar mountains are believed to have formed as a result of tectonic events. The concentration of Maria on the near side likely reflects the substantially thicker crust of the highlands of the far side, which may have formed in a slow-velocity impact of a second moon of Earth a few tens of millions of years after their formation. The other major geologic process that has affected the moon's surface is impact cratering, with craters formed when asteroids and comets collide with the lunar surface. There are estimated to be roughly 300,000 craters wider than 1 kilometer (0.6 mi) on the moon's near side alone. The lunar geologic timescale is based on the most prominent impact events, including Nectaris, Imbrium, and Orientale, structures characterized by multiple rings of uplifted material between hundreds and thousands of kilometers in diameter and associated with a broad apron of ejected deposits that form a regional stratigraphic horizon. The lack of an atmosphere, weather and recent geological processes mean that many of these craters are well preserved. Although only a few multi-ring basins have been definitively dated, they are useful for assigning relative ages. Because impact craters accumulate at a nearly constant rate, counting the number of craters per unit area can be used to estimate the age of the surface. The radiometric ages of impact melted rocks collected during the Apollo missions cluster between 3.8 and 4.1 billion years old. This has been used to propose a late heavy bombardment of impacts. Blanketed on top of the moon's crust is a highly comminuted, broken into ever smaller particles, and impact garden surface layer called regolith, formed by impact processes. The finer regolith, the lunar soil of silicon dioxide glass, has a texture resembling snow and a scent resembling spent gunpowder. The regolith of older surfaces is generally thicker than for younger surfaces. It varies in thickness from 10-20 kilometers (6.2-12.4 mi) in the highlands and 3-5 kilometers (1.93.1 mi) in the Maria. Beneath the finely comminuted regolith layer is the megaregolith, a layer of highly fractured bedrock many kilometers thick. Comparison of high-resolution images obtained by the Lunar Reconnaissance Orbiter has shown a contemporary crater production rate significantly higher than previously estimated. A secondary cratering process caused by distal ejecta is thought to churn the top 2 centimeters of regolith 100 times more quickly than previous models suggested on a timescale of 81,000 years. Lunar swirls. Lunar swirls are enigmatic features found across the moon's surface. They are characterized by a high albedo, appear optically immature, i.e. the optical characteristics of a relatively young regolith, and have often a sinuous shape. Their shape is often accentuated by low albedo regions that wind between the bright swirls. Presence of water. Liquid water cannot persist on the lunar surface. When exposed to solar radiation, water quickly decomposes through a process known as photodissociation and is lost to space. However, since the 1960s, scientists have hypothesized that water ice may be deposited by impacting comets or possibly produced by the reaction of oxygen-rich lunar rocks and hydrogen from solar wind, leaving traces of water which could possibly persist in cold, permanently shadowed craters at either pole on the moon. Computer simulations suggest that up to 14,000 km2, 5,400 sq-mi of the surface may be in permanent shadow. The presence of usable quantities of water on the moon is an important factor in rendering lunar habitation as a cost-effective plan. The alternative of transporting water from Earth would be prohibitively expensive. In years since, signatures of water have been found to exist on the lunar surface. In 1994, the bistatic radar experiment located on the Clementine spacecraft indicated the existence of small frozen pockets of water close to the surface. However, later radar observations by Arecibo suggest these findings may rather be rocks ejected from young impact craters. In 1998, the neutron spectrometer on the Lunar Prospector spacecraft showed that high concentrations of hydrogen are present in the first meter of depth in the regolith near the polar regions. Volcanic lava beads, brought back to Earth aboard Apollo 15, showed small amounts of water in their interior. The 2008 Chandrayaan-1 spacecraft has since confirmed the existence of surface water ice using the on-board moon mineralogy mapper. The spectrometer observed absorption lines common to hydroxyl in reflected sunlight, providing evidence of large quantities of water ice on the lunar surface. The spacecraft showed that concentrations may possibly be as high as 1,000 ppm. Using the mapper's reflectance spectra, indirect lighting of areas in shadow confirmed water ice within 20 degrees latitude of both poles in 2018. In 2009, LCROSS sent a 2,300 kilograms (5,100 pounds) impactor into a permanently shadowed polar crater and detected at least 100 kilograms (220 pounds) of water in a plume of ejected material. Another examination of the LCROSS data showed the amount of detected water to be closer to 155 plus or minus 12 kilograms, 342 plus or minus 26 pounds. In May 2011, 615.14 10 ppm water in melt inclusions in lunar sample 74,220 was reported, the famous high titanium orange glass soil of volcanic origin, collected during the Apollo 17 mission in 1972. The inclusions were formed during explosive eruptions on the Moon approximately 3.7 billion years ago. This concentration is comparable with that of magma in Earth's upper mantle. Although of considerable selenological interest, this announcement affords little comfort to would-be lunar colonists. The sample originated many kilometers below the surface, and the inclusions are so difficult to access that it took 39 years to find them with a state-of-the-art ion microprobe instrument. Analysis of the findings of the Moon Mineralogy Mapper (M3) revealed in August 2018 for the first time definitive evidence for water ice on the lunar surface. The data revealed the distinct reflective signatures of water ice as opposed to dust and other reflective substances. The ice deposits were found on the north and south poles, although it is more abundant in the south, where water is trapped in permanently shadowed craters and crevices, allowing it to persist as ice on the surface since they are shielded from the sun.